All right, good morning, Chem 30s. Let's see if we can't finish off chapter 14.2 and put this chapter to bed here with lesson 2, taking a look at your standard cells and your standard cell potentials. You guys have been spending a ton of time building these cells, at least on paper, labeling them, using your entities, identifying where electrons would go, where oxidation reduction would happen in your anode and cathode respectively. You were trying to label this with cell notation, so you should have a pretty good working idea of what the cells look like now. The one thing we've ignored so far is this idea of a standard cell potential, in other words, our voltage. Any battery or cell that we actually work with has a voltage rating to it. So there's obviously some energy or some work that can be done with these batteries. That's kind of the whole point, right? You have chemical energy, and you want to access it in the form of electrical energy and do some work like run your cell phone and video games and what have you. So you can get into much more detail about how this potential energy or this whole voltage idea works in Physics 30, but we can kind of simplify it back to our OA, RA, even going so far back as electronegativity. Remember that there is always a fight for the electrons going on here. All right, so when we're taking a look at the energy that we have or the work that can be done, it's almost a measurement of the strength or the pull that the OA has for the electrons in the RA. Remember that we have said that the RA will give up electrons to the OA because the OA has a greater affinity for them. So we can measure this. Now, one of the problems in electrochemistry and electricity as a whole is to define a 0 point is much more challenging than it was with gravity. In gravity, we always assumed a 0 point for potential energy as the floor or ground. While we could have chosen the roof or a tabletop, and sometimes both of those made sense, there was kind of a standard easy thing, and if this little speech makes sense to you, we should remember usually defining ground or the floor as your 0 point. In electrochemistry, the 0 point, or in electricity, the 0 point is hard to define. It's got ties to infinity, so we don't want to go into that at all. So what did we do? We have all of these various reduction potentials on our data sheet, and so we just had to arbitrarily pick a 0 point. This is no different than what Fahrenheit and Celsius did on a temperature scale. They just arbitrarily picked 0 points. And so we have picked an arbitrary 0 point for chemistry here as the hydrogen reduction half reaction. That means all other pulls or pulls on electrons that you have, pushes or pulls, I should say, all right, is just better or worse than hydrogen. So hydrogen becomes our 0 point. This assumes, of course, all standard conditions. Again, all of this stuff is listed at the bottom of your table. Okay, so we're looking standard 1 molar solutions at 1 atmosphere and 25 degrees. When we measure these potential differences or these energy differences, okay, we should be using the term potential difference, but industrially we also use the term the volt. And so we see that again on your table, electrical potential difference, also shown as voltage. So the two terms can be used synonymously. We do slide towards voltage a lot more here in chem. We will measure these empirically. If we were still able to get together and do labs, all right, that little V that we've been putting into all of our diagrams to measure how much energy is there when we trick the electrons to go through the wire would be measured with this. Theoretically, though, this is what we're working on today, is we're going to try and determine what is the theoretical voltage based upon, again, all of these standards that we see listed along the margin of your reduction table. So a couple of important things to remember. This is just the pull by OA to RA if we simplify it down to that. So it doesn't matter how much OA you have or how much RA you have, the pull will still be the same. Remember that all atoms and ions are identical to each other for the same species. So huge thing to remember right here, that potential difference or voltage is not stoichiometric. While you might balance the redox equation by multiplying, dividing, and doing all those things, we will do none of that to our potentials and our voltages. They are absolutes. So please do not multiply cell potential by any coefficients that you are adding. We also have to remember that our table is a reduction reaction table, so everything is shown as the gain of electrons. Well, in some of our half reactions, those oxidation ones, we were losing electrons. So if we're going to stick to what we have learned so far, that we had reduction plus oxidation in all of our cell notations, remember to flip and change the sign if you're going to stick to it that way. If we get a positive cell potential, this is another way that we can interpret spontaneity. So if you get a positive voltage, this is a battery. If you get a negative voltage, this is something that needs charging. Now, if you don't like reduction plus sign flip oxidation, there is another way around it. Your textbook shows this, so I feel I must have to do it as well. If you just wanted to use the reduction potentials off of your data table, you can certainly do that. You just have to memorize this formula as a little bit different than what we're doing, and it's cathode minus anode. Now, you might remember that as we've been setting up all of our practice problems, we've been trying to do it with a ton of information about what is SOA, what is reduced, what is the cathode, and vice versa, what is oxidized, loses electrons, and the anodes. So all of that information should be really easy to do with the entities method that we have been employing. The challenge is you need to pick one. You can either do cathode minus anode. However, with all of our entity stuff so far, we've been adding things. So personally, I like reduction plus the sign flip of oxidation. Both are absolutely equivalent and the same thing. All right, quick little example here. We did take a look at the silver-copper voltaic cell. We've drawn that one previously, and so we can take a look at which one is getting reduced and which one is getting oxidized. When we zoom in on the table here a little bit, okay, you can see that silver ions are the ones that are undergoing reduction and therefore exist at the cathode. So we know which one is being reduced. Silver undergoes reduction, and you can see its voltage right here is positive 0.80 volts. Oops, a little too zoomed in. When we take a look at our copper, copper was the one that ended up being reduced. It was lower on the table, and so you can see its reduction potential here is positive 0.34. But if we're going to do this way, remember that you must sign flip your oxidation because it's a reduction table, and so this would be plus negative 0.34. All right, so if we're going to do that one, both of those were in the positive range. As we continue and kind of move on with this one then, we just have to summarize it. Let's zoom out here. All right, and so positive 0.80 plus negative 0.34, that's going to become a difference for us. I assume you guys know your integers fairly well. All right, so if we were to do this one, it's just 0.80 plus, you can put in the integer, negative 0.34, and you get a 0.46 positive voltage. So your total here is 0.46 volts. The positive tells us that it is spontaneous. Just to show you that the other way is just as valid if you don't like sign flipping, all right, we go back here, we had reduction always taking place at the cathode. This is always, 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 and so you have positive 0.80. This one, however, is a minus. We're doing our integers differently here. We've seen this before with the Hess's shortcut. And so we just put in our oxidation or anode reduction potential. And so that one is positive 0.34. Doesn't matter how it works out here, just so long as you're consistent with your integers or your sign flips. But 0.80 minus 0.34 gets you to the same 0.46 value. It is positive, and so still spontaneous. So you guys will have a choice on which way you choose to calculate these potentials. I would recommend you just pick one of the two and master it. Got a bunch of examples on the next page. We'll go through those in the next part of the lesson.